Now let us look at the postulates of valence bond theory. Okay, so valence bond theory given by Pauling and later optimized and developed by other scientists also. So the first postulate says that metal atom has, or a metal ion or a metal atom must have vacant sp and d orbitals to accept electrons, lone pair of electrons from ligands. The second postulate says that these vacant orbitals will have to undergo hybridization, and from hybrid orbitals, these hybrid orbitals will then overlap with the orbitals of the ligands which has electrons in them. So let's say suppose you have a metal having a vacant orbital and you have a ligand having an orbital with 2 electrons. So this will undergo overlap to form something like this, where there are 2 electrons, or at the same time you can also say this is a coordinate bond. So because of this overlap, co-ordination complexes are also known as coordinate covalent complexes, or this coordination bond is also known as coordinate covalent bond because of this overlap. Okay. Now, valence bond theory also defines ligands in 2 different types, namely strong and weak ligands. Now, strong ligands can cause pairing in the metal ions, pairing of electrons in the metal ions, and weak ligands cannot do so. What do I mean by pairing? So, pairing means, say suppose there is a metal ion having, say, 6 electrons, out of which 4 are unpaired. So if a strong ligand comes near it, it may cause that these electrons also becomes paired and you get 2 vacant orbitals. And why it is needed, we'll see in detail. Now, octahedral complexes are being defined on 2 different types. It may be sp3d2, that means sp and 3 are of the same shell. That means it is ns, np and nd. That are known as outer orbital octahedral complexes. But if it is happening that the d orbital is of the penultimate, that means n minus 1. This comes from n minus 1 d, ns and np. They are known as inner orbital because the d orbital is from the inner shell. Tetrahedral complexes can either be because of the hybridization of sp3 or sd3. Similarly, square planar can be dsp2 or sp2d. dsp2 will obviously be inner orbital square planar complex, and sp2d will be outer orbital square planar complex. Now, one drawback of Werner's theory was also it could not explain the magnetic properties. So, valence bond theory gives that magnetic moment mu, and this is only spin only magnetic moment, is equals to under root 4s into s plus 1, where s is your spin of unpaired electrons. Now, spin is equals to what? N by 2. That means n is number of unpaired electrons. So if you replace s by n, you would get mu is equals to under root n into n plus 2 Bohr magneton. Now, in a case of transition metals, maximum number of unpaired electron is 5. So let's say here we have n and here you have mu. So if it is 1, 2, 3, 4, 5. For 1 unpaired electron, it will be 1 into 1 plus 2, that is under root 3, which is 1.73. For 2 unpaired electrons, it will be, I think, that is under root 8. It should be somewhere 2.8, if I'm not wrong. Please check the values. If it is 3 unpaired electrons is under root 15, it should be somewhere 3. Or it should be somewhere, I think, it will be 2.6 something, and this should be 3.82, I guess. For 4 unpaired electrons, it will be 4.9, and for 5 unpaired electrons, it is 5.9. So it's not difficult to calculate these values, but I would suggest to memorize these values because in the questions it will be faster for you to answer such kind of questions. Okay. Now let us take a quick look at the orbitals of the metal ion which undergo hybridization to form different type of complexes. So suppose you have octahedral complex. Okay. So for octahedral complex, you can have sp3d2. So that means you need s orbital, you need px, py, pz, and at the same time you need dx square minus y square and dz square. Why only these orbitals? Now, complexes are directional in nature. That is one of the reasons, one of the drawbacks of Valence theory. It could not explain why the secondary valencies are directional or pointed towards specific directions in space. It is because, as valence bond theory says, that overlap has to happen with the ligand orbitals, and these ligands are approaching along the axis. So only those orbitals of the metal ion can take part in hybridization which are directed towards the axis. So px, py, pz, dx square minus y square and dz squares are the only axes from sp and d which are directed towards, which are along any axis. So that is why they take part in the hybridization for octahedral complex. Now, say for example, we have tetrahedral complex. For tetrahedral complex, it may be s, px, py, pz, or it may be x, dxy, dyz, dzx. Now it is understood for the sp3-1, but for sd3, dxy, dyz, dzx. So that is because for a tetrahedral complex, the tetrahedral structure, none of the it is not possible for all the three bonds to be along three axes. Let us say all of the four bonds to be along three axes. The maximum you can make is one bond to be along an axis, but the other three will always be out of the axis. So that is why we take those orbitals which are somewhere in between the axes. So that is better overlap is there. That is why we have dxy, dyz, dz. More details you can find in any textbook which talks about chemical bonding. Then we have square planar complex. Now, square planar complex will involve s, px, py, and d x square minus y square, because all of these are again directed or along the axis. Okay, fine. Now we'll look at some of the examples of complexes, some exceptions, and some special cases for coordination complexes from the point of view of valence bond theory. So now let us take a look at some of the examples and try to explain the structure of the complexes from the point of view of valence bond theory. So we have, say for example, octahedral complex of COCl6 3+. Now Cl is a weak ligand. Cobalt in this case is in +3 oxidation state. Okay, so in cobalt in +3 oxidation state will have a configuration of 3d6. So that means the orbitals will look something like this. And then you will have 4s and 4p. Okay. Now this is in free state when there is no ligand near it. Now in a hybridized state also, because Cl is a weak ligand, it will not cause any pairing in this, but what will happen is, okay, it will undergo hybridization from 4s, 4p and 4d. So you have sp3d2, which is an example of outer orbital octahedral complex. So there will be 6 pair of electrons from 6 Cl minus ligands. Now, instead of a weak ligand, let us take the example of a strong ligand. That means, let's say we are taking COCN6, 3, okay, this will be 3 minus, 3 minus. So again, cobalt in +3 state, it will be 3d6. The free state remains the same. What will happen in hybridized state is that there will be a pairing of these two electrons because of cyanide. So this will change to and 2 vacant. Now these two vacant will undergo hybridization with 4s and 4p. This is 3d, 4s, 4p. And these will accept the lone pair of electrons coming from 6 Cn minus ions. Now this is n minus 1d, so this is an inner orbital octahedral complex. Now, how does the complex decide that how many pairing of electrons will occur for a particular compound? So that depends on the type of complex it wants to form. Like for an octahedral complex, you need 2 d orbitals. So it will always try to vacate 2 d orbitals, and it will try and it will do the pairing as many times it is needed to vacate 2 d orbitals. Let us say if you have VCN6 3 minus. So vanadium is in +3 state. In +3 state, it is having configuration of 3d2. That means it will have this configuration. Now there are already 2 vacant orbitals present. It need not do the pairing of these two to form an octahedral complex. It can use these two orbitals to form dsp2, d2sp3, and it will form an octahedral complex. So pairing will happen as only when you need to vacate 2 d orbitals to form the complex. Okay. There is a special case of COCN6 4 minus. In this case, cobalt is in +2 state. It will have configuration 3d7. So in free state, the electronic configuration is like this, and this is 3d, this is 4s, this is 4p, and you have 4d. Now in hybridized state, when there is an approach of cyanide ion or cyanide ligands, what will happen is there will be a pairing. Even after causing a pairing, there is only one orbital which is vacant, and it cannot use only one orbital to form octahedral complex. So it needs both of them. So what happens is that this is shifted to 4d, and this gets vacant, this comes here, and all of these undergo hybridization to form d2sp3, that means outer orbital octahedral complex. Now, what is the evidence that this kind of a transition is occurring from 3d to 4d? Now, 4d is a higher energy orbital. Now, if you excite an electron to higher orbitals, higher energy, it will be beneficial or for the complex to release that electron so that it can come to a lower energized state. So that means this will behave as a good reducing agent. Okay, fine. Okay, now let us say, okay, so fine. Let us take the example of a tetrahedral complex. Okay, so there is one more exception, or this was an exception of coordination compounds. Since you are studying inorganic chemistry, there will be exceptions in special cases. There is one more for cobalt ammonia complex. It should be not cobalt ammonia, it should be cobalt water. Okay, so Water is not a very strong ligand, neither a very weak ligand. It's a moderate ligand. But valence bond theory does not speak about moderate ligands. So let us say it is not a strong ligand, so let's consider it a weak ligand, and you would expect that 3d6 you don't expect pairing to occur in this case. But cobalt 3 hexa aqua complex is a special case where pairing will occur and you will get inner orbital octahedral complex. Okay. Now let us take a look at tetrahedral and square planar complexes and then we'll move on to the questions that we have from valence bond theory of coordination complexes. Now let us take some examples of tetrahedral complexes. Say for example you have CuCl4 2 minus. Cobalt is in +2 state 3d7. So it will have in free state okay. Now because chloride is a weak ligand, it cannot cause pairing. It will use these orbitals to form habit orbitals for tetrahedral complex. Now let's say we have a strong ligand, cyanide. So again cobalt is in +2 state d7. So now this is the free state 3d 4s 4p, but because of the cyanide there will be one pairing to give you this complex, this kind of electronic configuration. You have one vacant 3d 4s and 4p. So these will undergo hybridization to form dsp2 and this will be a square planar complex. So there are actually questions like this. Depending on the charge and depending on the ligand, the structure of the complex is also determined. Okay, so there is one more exception to this, is NiCN4. Nickel is in +2 state, that is D8. Now again you would expect that the electronic configuration in free state looks like this. So in presence of cyanide it should undergo overlap to give you this one vacant 3D and it should form a square planar complex, but that does not happen. This pairing does not occur. This remains like this, and 4s 4p, it forms a tetrahedral complex. This is an exception for this. There is a special case which is of copper ammonia complex. Copper in +2 state has 3d9 configuration. So in the free state it will look something like this. You have 4s and 4p. So so there is no use of vacating this. Okay, so you cannot do pairing here. So you would expect that it will have tetrahedral geometry. But X-ray studies say that it has square planar geometry. Okay, fine. So we had seen one example when the electron was shifted to higher energy orbital. So if that is true, if this was indeed happening, so that means my configuration will look something like this, and this will form dsp2. So in that case, that was a very good reducing agent. So it should point out that this is a good reducing agent, and this CuNH3 2 plus should change to CuNH3 3 plus because of releasing one electron, but that reaction is also not happening. this reaction does not take place. So that means this shift is not happening. So how is it forming a square planar complex? So the hypothesis that was put forth was this unpaired electron remains in 3D, but the orbitals which take part in the formation of hybrid orbitals are 1s, 2p and 1d. This is an example of PD mixing. Okay, and this is why it forms a square planar complex. Okay, this is a special case for copper complex. Now let us take a look at the limitations that we have for valence bond theory, then we'll discuss the questions that have come previously. So the first limitation is nature of the ligands. It does classify the ligands as a weak ligand and strong ligand, but it does not say on what basis the category is being done. Secondly, the pairing of electrons. It says that when there is a strong ligand, electrons will pair, but why will that happen? There is no explanation given for that also. Then there is spectra. There is no mention of the electronic and color spectra or how we justify the different spectra that we get for the coordination complexes. Deviation in magnetic moment. Now, you have been given a formula for the spin-only magnetic moment, but there are certain complexes in which there is very good deviation from this formula or this spin-only calculated magnetic moment, and why the deviation is occurring. Then there is no explanation for the effect of temperature on magnetic moment and magnetic susceptibility. How temperature is affecting the magnetic moment of a particular complex. There is no explanation to the kinetics and the reaction mechanism for complexes, and at the same time why this kind of a structure will form for copper ammonia complex. So there are no explanation given for the special cases also in case of valence bond theory, which is what we'll see in the next lecture when we discuss about crystal field theory. Now we'll quickly go through the questions that have come from this part of coordination chemistry, and then we'll be finished. We'll be over with this valence bond theory of coordination complexes. So the first question we have is long back from GATE 2007. Now they are saying the structure of the complex CuNH3O4Cl O4 and CuNH3O4 Cl O4. So if you see in the first case, the complex has a charge of +2, and in the second case the complex has a charge of +1. So that means copper has +2 charge, copper has +1 charge. Now copper in +2 charge will be D9 and copper in +1 charge will be D9, 3D9, 4S1. This will change to 3D10. Now if it is 3D10, there are 2 unpaired electrons and the orbital is fully filled, so it will try to remain as that. So here the hybridization will be something like this. Only the 4s and 4p orbitals will go hybridization to form tetrahedral complex. But in case of D9, as we have seen, this forms a square planar complex. So the correct option for this will be option number A. Okay. So there is another question which came in TIFR 2017. The given molecular formula of hexa-coordinated complexes. So you are given 3 complexes, and they are also saying if the number of coordinated NH3 molecules is 1, 2 and 3, respectively R6, 5 and 4, the oxidation states of cobalt. Okay, so you have in the first complex there are 6 ammonia, so it is CO NH3 whole 6 Cl3. In the second one it is 5 and in the third one it is 4. So the charge here is +3, +2, +1. How I am getting the charge? There are 3 Cl minus ions, so -3 for 3 minus ions, and since entirely it is neutral, so the complex will have +3 charge. And this charge will be on this, Again, in this case, this is -1, so this has to be +3. This is -2, this has to be +3. So that means there is no change in the charge of the complex. The correct answer is option number D. So I don't think any more questions are there from this part of the coordination chemistry. This was needed to create the basics for the next topic that we'll be discussing in the next video, that is crystal field theory, which is one of the very important topics for coordination chemistry in all exams, either it's NET, GATE, TIFR, JAM or any entrance exams. So we'll see, I'll see you in the next video.